Welcome back. I would like to look at another example of graphing a rational function. This one is going to look markedly different from the one that we did in the previous video. So starting from the top, we would like to determine the domain, so I will see if I can factor this any further. This is x minus 16 over... Now I have a difference of squares in the denominator, so I could factor the denominator as x plus 2 x minus 2, and again it doesn't look like anything will cancel on us. So to determine the domain, now you always want to pick out the domain before you cancel anything, so that's why cancellation, reducing the fraction, is the second step. Domain always comes first. So if I set the denominator equal to 0, when is x plus 2 times x minus 2 equal to 0? Well, that happens when x equals negative 2 or positive 2. And so those are the x values that we cannot plug into our function. So x cannot be positive or negative 2. Any other x value will work, so our function exists everywhere, horizontally speaking, except at x equals positive and negative 2. So again, this function will not cancel, or I should say nothing will cancel in this function. The x plus 2, x minus 2, and x minus 16 have nothing in common. So I can move straight into finding my intercepts. Okay. I usually like to start with the y-intercept first. So I'll let x be 0 and see what happens. So if x is 0, I have 0 minus 16 over, and it's probably going to be easiest to plug it into my original function. So I'll do 0 squared minus 4, since nothing canceled. Now if something had canceled, I would want to plug it into the reduced version of the function, because that would be simpler. So finally, 0 minus 16 is negative 16 over 0 minus 4, negative 4. And our y-intercept is at a height of 4. And then we can find our x-intercepts by setting our function equal to 0. Now again, since my function did not reduce at all, I think I'll use the original version for this. Now, there's no harm in using the factored form. I just happen to know this is going to take a little bit less time if I do it this way. Alright, so the way that I would solve this would be to multiply both sides by the denominator, so 0 times x squared minus 4 equals x minus 16 over x squared minus 4 times x squared minus 4, and we see these cancel out. And on the left-hand side, I'm multiplying a bunch of stuff by 0, so 0 equals x minus 16. And finally, this equation is very easy to solve. If I add 16 to both sides, I find x. So it looks as though my x-intercept is 16, 0. And in particular, this is useful because I know that it will not cross the x-axis anywhere else. So finding these intercepts tells me my function is going to be stuck above or below everywhere else. And we'll find the vertical and horizontal asymptotes to see what effect they have on the graph. Now there's no one particular asymptote you need to look for first. I usually go for the vertical asymptotes because I've already done most of the work when I talk about the domain. So remember, this is the reduced form, so I can set the denominator x plus 2, x minus 2 equal to 0. And I see that this happens when x equals negative 2 and x equals 2. So we see what is going on at those two areas of concern with respect to the domain, those are both vertical asymptotes. Now, in a couple of videos, I will explain one other possibility. We don't always have a vertical asymptote at these critical numbers, at these points that are excluded from the domain. There is something else that can happen, and that's why I always want to use the reduced form of the denominator to find these vertical asymptotes. So that is important, and we'll talk more about that later. Now I need to find the horizontal asymptote. We found the vertical asymptotes. There are two of them. And now we'll figure out first if we have a horizontal asymptote, and then where it is if we do. Or we might be dealing with a slant asymptote. So in either case, we'll be able to find that other type of asymptote. Now my function has a numerator of degree 1 and a denominator of degree 2. So this is that first case that we saw where the degree of the numerator is less than the degree of the denominator, and so our horizontal asymptote is just going to be the x-axis. This is the nice one. If that degree on the top is less than the degree on the bottom, we don't have to do any work. So once I find my horizontal asymptote, I'd like to know, does my function cross? Sorry, we're calling this g of x. Does it cross the horizontal asymptote? Now, we have actually already answered this question. Remember, the horizontal asymptote here is the x-axis. So if I ask this a little bit differently, I could say, does g of x cross the x-axis? And we've already looked at whether or not this happens when we asked about the x-intercept. So yes, we already did the work, and it happens at 16, 0. So sometimes you can get around having to set your equation equal to the horizontal asymptote if you've already done that work. But generally speaking, we would have said, alright, let's take our function x minus 16 over x squared minus 4 and set that equal to our horizontal asymptote, which was 0. So you can see we already set that up and did all of the calculations. So I would like to begin including all of the information that I found so far, and I'll use a nice big axis for my graph. Okay. We know our y-intercept is at 4, so I'll let my tick marks be in steps of 2. There's our y-intercept. My x-intercept, 2, 4, 6, 8, 10, 2, 4, 16. And so that we can see that our horizontal asymptote is the x-axis, I'll extend my horizontal line along the length and extend it a little bit past the x-axis, just so you can tell that it's there. Now finally, we know our vertical and horizontal, or wait, I already talked about our horizontal asymptote, our vertical asymptotes at positive and negative 2. So negative 2 right there, and positive 2. Now in the next video, we will plot a few additional points and complete the graph of this function.